We want to find the area of the region enclosed by the curve given by the parametric equations x equals t minus t to the fourth and y equals t minus t to the seventh when t is on the closed interval from 0 to 1. We want to use Green's theorem to determine this area. So the first thing we should recognize is that the area of a region in a plane is given by this double integral, where we'd have the double integral over the region R of 1 differential a. So if we recognize that this will give us the area of a region R in a plane, then we want to explain why this is equal to this line integral here, where we have 1/2 times the line integral along the curve C of negative y differential x plus x differential y. If we can explain why this makes sense, then we'll understand why Green's theorem can be applied to determine this area. So again, first recognizing that this double integral would give us the area of region R, and then comparing this to Green's theorem shown here, if we want this double integral to be equal to this double integral, the first thing we want to recognize is that we would need the difference of these two partial derivatives to be equal to 1. The next thing to notice is looking at the line integral, because we have negative y dx plus x dy, the vector field f would have an x component of negative y and a y component of x. So if we determine the partial derivatives using this vector field, notice the partial of q with respect to x would be 1, the partial of p with respect to y would be negative 1. So the difference of the two partial derivatives doesn't give us 1, which we want, it actually equals 2. And this is where the 1/2 comes into play in the formula. Because 1/2 times 2 equals 1, this is where we get our formula. The area is equal to 1/2 times the line integral of negative y dx plus x dy. Again, using the vector field shown here, the difference of the partial derivatives gives us 2, and because we need a 1 as the integrand function, we have this extra factor of 1/2 here. Now before we apply the formula though, we do want to make sure the curve C, given by the parametric equations, does satisfy Green's theorem. Where for review, the curve C must be a simply connected piecewise smooth curve with a positive or counterclockwise orientation that encloses a region R. Remember, if the curve C has a positive orientation, then the region R would always be on the left of the curve C. And I've already checked this. The curve given by the parametric equations would be traced out in this direction, and therefore it does have a positive orientation. So Green's theorem is satisfied. The curve C is a simply connected piecewise smooth curve with a positive orientation. Before we set up our line integral though, let's go ahead and write down the vector field f would have an x component of negative y and a y component of x. Let's also write the curve given by the parametric equations as a vector valued function r of t. So r of t would have an x component of t minus t to the fourth and a y component of t minus t to the seventh. And we're also going to need r prime of t, so let's go ahead and find that now. R prime of t is equal to, the x component would be 1 minus 4t to the third, and the y component would be 1 minus 7t to the sixth. So now we know the area is equal to 1/2 times the line integral along the curve C of negative y dx plus x dy. And now to evaluate this line integral in differential form, we can also think of this as 1/2 times the line integral of f dot differential r, which can be written as a single integral as the integral from a to b of f of x of t comma y of t dot r prime of t dt. So this is equal to 1/2 times the integral, and now f of x of t comma y of t would be, well, the x component of f is negative y, which is the opposite of t minus t to the seventh, so that'd be negative t plus t to the seventh. The y component is x, which is t minus t to the fourth, dotted with r prime of t, which we already found. R prime of t has an x component of 1 minus 4t to the third, and the y component is 1 minus 7t to the sixth. And we have differential t, and limits of integration for t are from 0 to 1. Let's evaluate this on the next slide. And now we'll find the dot product. So we have 1/2 times the integral from 0 to 1 of, we'd have the quantity negative t plus t to the 7th times the quantity 1 minus 4t to the 3rd plus the quantity t minus t to the 4th times the quantity 1 minus 7t to the 6th. And now we multiply. So here we'll have negative t plus 4t to the 4th plus t to the 7th, and then minus 4t to the 10th, plus the quantity, here we'll have t minus 7t to the 7th, minus t to the 4th, and plus 7t to the 10th. And now we'll combine like terms. So we'd have 1/2 times the integral from 0 to 1 of, starting with the highest degree terms, we have 3t to the 10th, and then minus 6t to the 7th, plus 3t to the 4th, and the t terms simplify out. And now we integrate with respect to t, so we have 1/2, the antiderivative is going to be 3/11 t to the 11th minus 6/8 t to the 8th plus 3/5 t to the 5th. And when t is 1, we'd have 3/11 minus 6/8 or minus 3/4 plus 3/5. And then when t is 0, all terms would be 0, so we'd have 0 minus 0 plus 0. So here we end up with 1/2 times 27 over 220. So the exact area is 27/440ths, which is approximately 0.0614. So going back to our graph just for a moment, we just found the area of the region R, or the area bounded by the curve C. I hope you found this helpful.